So far with covalent bonding and covalent compounds are molecules, we now know how to draw Lewis dot structures, which shows us exactly which atoms are connected to which, and also what kinds of bonds connect those atoms together, whether they're a single bond, a double bond, or a triple bond, right? We also know now about the VSEPR theory, the valence shell electron pair repulsion, that lets us know, depending on where these bonds are around each atom and what lone pairs an atom may have on it, you're going to have electron repulsion that will create some cool 3D shapes for these molecules. Okay, but now I want to zip on down and go back to the bonds themselves, maybe within the molecules, and talk about what that means in terms of polarity. So we're going to talk about two types of polarity today. We're going to talk about bond polarity, meaning if a bond within a molecule itself is polar, and then we're going to even talk about molecular polarity, which means in the entire molecule, can an entire molecule be polar or not? Now, polar stuff requires the term electronegativity. Now, we've kind of alluded to this before in last unit when we talked about ionic compounds being like, hey, yeah, ionic compounds are formed because there's a very large difference in electronegativity. Yes, we're going to really hit that hard today. As a result, let's review what electronegativity is. Electronegativity is the ability of an atom to attract an electron. And we know as it increases as you go across a period, because increasing nuclear charge, more protons are added, which means the electrons are able to be pulled in tighter. And it decreases as you go down a group, because as you go down a group, you add energy levels, meaning the electrons are not able to be held quite as tightly. Okay, so on our periodic table, I think in Unit 4, we had ourselves draw the electronegativity trends. Just keeping in mind that, guys, this top right corner of our tables here are the elements with the highest electronegativities, which you guys, look, those are the nonmetals. Weird. And then if I go down here to the bottom left corner, we get lower and lower and lower electronegativities on metals. Now we see the point of that staircase. That staircase really is the dividing line, yes, of metals and nonmetals, but what has determined metals and nonmetals is this electronegativity, which is really cool. Okay, so on our reference charts, and in fact, I'm going to show you, we have on the back of our periodic table, so your yellow periodic table page, right, that we all have. On the back, if you flip it to the back, you have this really fun thing that says electronegativities of the elements, and it's got all of your elements and their electronegativity values, which is really cool. So what I'm looking at here is all of the electronegativity values of all of the elements, excluding the noble gases. We talked about noble gases have no electronegativity. They are already stable. They have a complete octet. But I've got values for all of the other elements, right? And the electronegativities do not have a unit. They are on what is called a Pauling scale, so they are just numbers. But as I can see, fluorine's my most electronegative guy. He's got an electronegativity of 4. And as I get down to the bottom left, the electronegativity values get smaller and smaller, which is pretty cool. Okay, so what does this mean in terms of bonding? She's telling me like the differences in electronegativities. Okay, let's pretend we have two dogs that are sharing a bone and they're tugging on that bone like a game of tug of war, right? So if these two dogs are fighting over a bone, do they have equal strength? Probably not. I would say that this dog over here, he is much bigger. He's probably pulling on that bone a lot harder, right, than this little teeny tiny dog. Guys, atoms are the exact same way. Their differences in their electronegativities are the differences in the strengths of pulling on electrons. Well, how does this relate to bonding? Well, in covalent bonding, we know covalent bonds are made between two atoms that are sharing the electrons. But those atoms are pulling on the electrons. We talked about the nuclei of both atoms. The nucleus of each individual atom is positive, and they're pulling on their electrons. Now, those atoms may not be the same atom. One could be a carbon, one could be a fluorine. They're different electronegativities. If I looked on my chart, how would that affect the bond? So let's talk about bond polarity. Most bonds are a blend of ionic and covalent characteristics. The difference in electronegativity between the two atoms in the bond actually determines the bond type. So what we're looking at here, my y-axis as I move up here is showing an increasing difference in electronegativity. Meaning down here, if I don't got that much of a difference in electronegativity between the two atoms involved, I've got a nonpolar covalent bond, which we'll talk about what that means here in a second. And as I move up, meaning the differences in their electronegativities gets greater and greater as they are moving further and further and further apart from the on the periodic table, or if you have elements that are further and further spaced apart on the periodic table, they now get a maybe more polar covalent. And then if they get even further and further away, a higher and higher difference in electronegativity between the two atoms, now we've got a transfer and not a share anymore to where that bond type will become ionic. Okay. Now, there are some benchmark threshold values that will determine at what point do you switch from being non-polar covalent to polar covalent to ionic. Now, these numbers that you see here are not absolutes. This is kind of a general thing because this is a spectrum, you guys, okay? But these are the ones we'll be using for my class. Most textbooks and chemistry courses will have numbers that are very similar to these. But just do not freak out if you're like, oh, I saw somebody say, instead of 0.2, 0.5. It's fine. We can all play nice with each other in the game of chemistry, but this is just to distinguish between a different style of bond, okay? So if my electronegativity difference between the two atoms is equal to or less than 0.2, I've got a nonpolar covalent bond. If my electronegativity difference is bigger than 0.2, but not any bigger than 1.7, I'm still sharing, but now I'm a polar covalent bond. And then finally, if my electronegativity difference is so much bigger than 1.7, I've got a transfer and ionic bond. So what does that look like for me? I love these pictures. So what these pictures are showing you is the bubble regions are showing the regions of electron density between two atoms in these three distinguishing bond types. This first example is a non-polar covalent bond, okay? Here, this little black dot represents the nucleus of one atom, and this is the nucleus of the other atom in the bond. And if I'm looking at this, it looks like the electrons are shared equally. There's a symmetrical distribution in the electrons. Not one of these two atoms is pulling on the electrons harder than the other. And that is due to them having a very small difference in electronegativity. Both of these guys are like, yep, we like them about the same amount, so we're pulling on them equally, okay? Now, my second type, my polar, oh, look at this. This side of my bond is a little bit more bubbly. That just means the electrons are being pulled more favorably to that atom. This atom on this side is more electronegative than the atom on the other side, okay? So as a result of this difference in electronegativity being somewhat significant, you're going to have a polar covalent bond where one atom is pulling more strongly on that shared pair of electrons. And then finally, they're not even connected anymore. Well, that is because one atom has a much, much greater difference in much, much higher electronegativity to where that difference is so large that transfer will happen. Now we're going to watch a real fun, real quick demonstration showing specifically the differences between nonpolar and polar covalent bonds, kind of in the visualization of like a game of tug of war.
Covalent bonds occur between nonmetals since they have the same or similar electronegativity values. In an H2 molecule, both atoms have the same electronegativity values. It's like hydrogen is facing a clone of itself in a tug-of-war match, so it ends in a tie. The shared pair of electrons split their time evenly between the valence shell of each hydrogen atom, giving both atoms a valence shell that's complete. When the electrons are shared evenly, it's called a nonpolar covalent bond. In an HCl molecule, chlorine has the higher electronegativity value, making it the stronger opponent. Chlorine isn't quite strong enough to completely pull the electron over to its side, but the electron pair spends more of its time on chlorine's side. This uneven sharing of the electron pair causes chlorine to carry a partial negative charge and hydrogen to carry a partial positive charge. When the electrons are shared unequally, it's called a polar covalent bond.
I love that animation with the tug of war. I think it really kind of drives home the point of what an equal sharing or an unequal sharing of electrons looks like. Okay, so now we got some practice. Like I mentioned, we have our chart of electronegativities on the back, and I can actually use this to kind of calculate my difference in electronegativity, and based on those threshold values I've given you, identify which of my 3 types I am. So, whoops, I zoomed out. I needed to zoom in. Okay, so I've got HBr, or hydrobromic acid. If I find hydrogen, he's got an electronegativity of 2.2. And then I've got bromine, he's got an electronegativity of 3.0. So the difference in electronegativity between the 2 atoms in HBr is going to be 0.8. That would put us into the polar covalent bond territory, where yes, they are sharing their electrons, right? But that bromine, being more electronegative, is sharing it a little bit more unequally, and so those electrons will be pulled more closely to the bromine side. Next one over, I got sodium fluoride. Y'all are like, already it's an ionic bond. We know, we don't need no numbers. Well, let's use the numbers to prove it to us, okay? We know, yes, sodium is a metal and fluorine is a nonmetal, and that's our ionic bond. But if I look at the electronegativity differences, sodium with its 0.9 and fluorine with its 4, yeah, the difference is a 3.1, which puts us well into the ionic bond side. And then I've got N2, which is my diatomic nitrogen. So this is what nitrogen exists as. It's just 2 nitrogens stacked together. Well, what's the difference in electronegativity if they're the same? Well, there is not. It's just 2 atoms of nitrogen both having the same electronegativities of 3. So the difference is 0. This is a nonpolar covalent bond. So now let's dive into and look at these visuals here on the nonpolar covalent bonds. We have, in a nonpolar covalent bond, the electrons are shared equally. And here we also see that symmetrical electron density that we were talking about before, right? Where neither one of the 2 atoms are pulling more strongly on the shared pair of electrons. And because neither one of the atoms are pulling more strongly than the other, it tends to be made from identical atoms, these nonpolar covalent bonds. So an example, if I wanted to write underneath my cute little bubbly nonpolar covalent bond, is I would write what elements are involved in this bond. And our elements, our molecule from the previous slide that we were talking about that calculated out to be a nonpolar covalent, was the N2, the nitrogen molecule. So we could say that these 2 guys are both atoms of nitrogen, forming a nonpolar covalent bond. So my second bond type, a little bit more going on here, I know, is a polar covalent bond. That's where the electrons are shared unequally, where you create this asymmetrical electron density. Like in our hydrobromic acid, bromine was more electronegative, so he pulled on the electrons more. Now, what this actually does is it results in something called a partial charge dipole. So I've got this big old weird arrow here drawn across my bond. My dipole arrow is drawn towards the atom that has a higher electronegativity, or the way I like to think of it about it, towards the atom that wants the electrons more, where the electrons are going, basically. Now, if you'll notice, the opposite end of the arrow is like a dash behind it. This is important because this shows us where the partial charges are within the molecule. Here we've got the Greek symbol delta. On this side next to the bromine atom, I've got a delta minus. And on this side next to the hydrogen atom, I've got a delta plus. That means a partial positive. This is not a full, complete transfer of electrons where I've got 2 bonds, a cation and an anion, like I would see for ionic bonds. They're still sharing, so nobody is truly positive or negative, but I've got this partial positive and negative charge because of this unequal distribution of the electrons called the dipole. Let's talk a little bit more about this dipole. So polar covalent bonds, they're still molecules, they still share their electrons, but because the electrons are unequally shared, one atom has a stronger pull on the electrons than the other. So in HBr, the electrons are more attracted to the bromine atom, which results in a partial negative charge. This distribution of partial negative and partial positive charge in the bonding region is called a dipole moment, okay? So now I thought we could look at some other dipole moment examples, okay? So this is HBr right here. And we, with our electronegativities, can actually prove that this would calculate out to be a polar covalent bond. So I would find hydrogen. He's right here. He's got a 2.2. His electronegativity is 2.2. And then I've got bromine. He's down here. He's got a 3.0. So their difference in electronegativity is 0.8. Here's another example. I've got CH. I've got carbon and I've got hydrogen. Carbon, he's right here. He's a 2.6. Hydrogen, he's over here again. He's a 2.2. Now, their difference in electronegativity is not quite as great as the first example, but there is still a slight larger pull on the electrons coming from the carbon than there is on the hydrogen. So you can see how I have the dipole drawn along this bond line as well for this other example of a polar covalent molecule. Okay, now we've got my ionic bonds. Now my ionic bonds are where their differences in electronegativities are so great. I'm talking about them being like on other planets here. Okay, to where the electrons are transferred completely to the more electronegative atom. And this is going to result in cations and anions. So an example of an ionic bond would be sodium fluoride, okay? And here, notice I've not only just written the names of the elements involved, but I've also showed, yeah, now not only is this a sodium atom, he ain't an atom anymore, he's a true ion because he has transferred his electrons over to the fluoride ion, who is an anion now, which we love. Okay, so let's talk now about, actually, I think I want to show y'all something. Let's do this. Okay, so we've got my electronegativity chart, and that was all good and fun. We've got, this would be an example of a non-polar covalent bond. If you're noticing, I have atoms that are exactly the same. Here is what a polar covalent bond actually looks like. First of all, I've replaced one of the atoms with now a green one. I'm going to say that green one is maybe somebody like bromine, who's got a much higher electronegativity value than somebody like a hydrogen. So this could be hydrobromic acid, HBr, like from our example. Now, what we notice here, instead of having a little gray flat or straight bond connector thing here, I've got this type of a bond shape. So what this is showing here is this is showing that dipole, or which direction in that bond the electrons tend to more likely be found in. That also lets me know that this guy right here is more electronegative because the electrons are being pulled more towards this green bromine than they are on that way, okay? And once again, I can visualize an ionic bond too. An ionic bond, they're not even connected at all. I've got a transfer from the metal to the nonmetal because the nonmetal has such a large difference in electronegativity that a transfer will occur, creating a negative anion and a positive cation. So I want to talk about, well, what does this mean for me? Because we know we have things like molecules where there's lots of different bonds in there. How does that affect the molecule, all of this polar talk? Well, I've got something to show y'all. Let's see. I have got, this is CH4, okay? And I've replaced the little plain gray bond sticks with now these ones that show polarity. So in CH4, each one of these white things are hydrogens, and the black guy is carbon, okay? Well, carbon's electronegativity is 2.6, and hydrogen's electronegativity is 2.2. That's a polar bond, right? So if he's got 4 of those, he's got 4 polar bonds. And I'm looking at this, oh my gosh, you are all 3D, and now you've got all these dipoles, and what is even happening here? We've also talked about like water and stuff, you guys. And this is gonna freak y'all out. So we've got our water guy. In fact, I'm gonna not scare y'all. We're gonna start small. This is a water molecule, yes. I'm gonna change him a little bit. Boom. Now this is helping me out a little bit more in terms of what's going on with the electrons here. These two guys on top, these little ears, those are the lone pairs that we now know water actually has that gives him this bent Vesper shape. But in addition to that, you guys, there's hydrogen and oxygen bond here and a hydrogen and oxygen bond here. Oxygen is more electronegative than hydrogen. So that is a polar bond with a dipole pointing towards oxygen and another polar bond with a dipole pointing towards oxygen. How does that affect this molecule and how it behaves? That was a giant tangent, but that was a giant tangent. Let's talk about this. Y'all, the different bond polarities can affect an entire molecule. So here we're going to talk about molecular polarity. Can entire molecules show polarity? Yes. The overall molecular dipole moment, or molecular polarity, describes a molecule's net dipole, which is the collective sum of all of the individual bond dipole moments within the molecule. A molecule is polar if it has polar bonds and the individual bond dipoles do not cancel each other out. Whoa, what is going on here? Let's bring out my molecules again. This is so super fun. So as I mentioned, you guys, yeah, here's my water molecule. I've got a dipole here going towards the more electronegative oxygen from this bond. I've got a dipole here going towards this more electronegative. And as a result, I have this pulling up in this direction of negative charge. Okay? Whoa. Not only do I have that coming from the bonds, I've got literal negative lone pairs up here to where if this molecule were like a battery with a north pole and a south pole, right? It's got more of a negative end up here to the molecule, and down here on the other end, he's more positive over here. So it kind of acts like he's like a magnet in some sort, or a battery, okay? Now I also have this example here where I have CO2. Here it says dipole moments cancel out. So if I brought out an example of CO2, here's CO2. Once again, I've replaced the bond sticks with these polar bond sticks, right? Showing over here that oxygen must be the more electronegative atom between the bond and oxygen and carbon. Same thing here. So I've got polarity here. But the difference is that those dipoles, one dipole is going this way, one dipole is going this way. They are going in opposite directions completely. So those dipoles cancel each other out to where you don't have any net molecular dipole. Okay, you were like, y'all are probably, your heads is spinning and being like, what is going on here? So here's a visualization of my water molecule kind of again, right? A little bit different of a visualization. We said that overall here, we've got some positives coming here and that negative oxygen is coming here. And like, y'all, I can draw a dipole arrow for an entire molecule showing the general distribution of which end of a molecule is polar, or which end of the molecule is more negative, right? Near the oxygen, and which end of the molecule is more positive, near the hydrogens here. So I have a slightly negative end of my molecule and a slightly positive end of my molecule. And we will talk about how the polarity of water leads to a bunch of really fun characteristics in the spring semester, but I wanted to bring this up with water right now. Okay, so you are already like, what does she mean when the dipole moments cancel out? Luckily for us, we are not dealing with very complex VSEPR shapes to where to give us a situation where dipoles cancel out, we're going to see some kind of keynote things here. So if I'm a nonpolar molecule, you're going to see the outer atoms are going to be the same. And you're going to see that there's going to be no lone pairs on the central atom. If I have both of these two things, that molecule is going to be symmetrical, okay? Now for a polar molecule, you're going to see either different outer atoms or you're going to see lone pairs of the central atom. And if that happens, then you are not going to be symmetrical. That molecule will have a net dipole moment coming from it. So let me show you some examples here. I'm going to keep this up on the screen because I think it may be helpful. We showed carbon dioxide. He does not have any lone pairs on his central atom, making this linear shape be anything but linear, right? He is not bent or anything funny. And his two outer atoms are exactly the same. As a result, it's symmetrical. His individual dipole moments will cancel out. So he will be a nonpolar molecule. But if I bring water in here, y'all, yes, he's got the same outer atoms. Yes, they both hydrogens, but he does have lone pairs on the central atom, which means it's going to create this shape to where those dipoles now collectively go up together, creating a net negative charge here on the top of the water molecule where the oxygen is, and a net positive charge down here where the hydrogens are. So we have a polar molecule. You're like, okay, I need some more examples. Well, I have more examples for you. Here is ammonia. Once again, the little tan thing is a lone pair. If I want to hide him for a second, I've got a blue nitrogen attached to 3 hydrogens, okay? Now, this is actually a trigonal pyramidal shape, and the reason why I have this lone pair here is because that nitrogen has a lone pair of electrons on there, and that affects the shape, right? That means all of these arms are kind of kinked down a little bit to where I'm not flat like a little airplane propeller, okay? So because of that, and each one of these bonds are polar to where they're pulling towards that middle nitrogen, and this lone pair is also negative up here, so I would have a net dipole going up through here to the top of the nitrogen of negative charge. But I can go back to my rules. You're like, she just talked a lot. I did. But all I got to do is I got to check here. Are the outer atoms the same? Yes, but there's a lone pair on that atom. So here, because of that lone pair on the central atom, he is not symmetrical. I've created some sort of a net molecular dipole here, so I will be polar. Let's do another one real quick. This is getting fun. Okay, here I've got CH4, a carbon connected to 4 hydrogens. Well, according to my list here, they got the same outer atoms, and there are no lone pairs on my carbon here. So he's got to be a non-polar molecule. That's because each one of these individual bond lines are all canceling each other out to where I don't have a net molecular dipole happening here. But well, here's a fun game. But what if I were to replace one of these hydrogens on CH4 with something else? Oh, I've replaced one of the hydrogens with chlorine. Yes? Looking at this. Yes, the hydrogen to carbon bond line is going towards the carbon, where carbon is more electronegative. But now in the bond between carbon and chlorine, I'm going that way. So as a result, y'all, these bonds are not going to cancel each other out. I will have a net dipole going up towards the chlorine part of the molecule. So still satisfied here in my list. I've got no lone pairs on my carbon, but I have different outer atoms. And as a result of that, this will be a polar molecule. So the trend here is if you got to have two requirements in order for you to be polar. You've got to have the same outer atoms and no lone pairs on the central atom. If you got both of those two things, you're going to be non-polar. But if you have either different outer atoms or you have lone pair or lone pairs on the central atom, you will be polar because the electron distribution of the dipoles is not going to be symmetrical. Okay, so that was super fun. That was our lesson on not only bond polarity in order to determine whether a bond is either non-polar covalent, polar covalent, or full ionic, but we looked at how all of those individual bonds and their polarities can come together and create the polarity of an overall molecule.